Okay, this is the lecture for October 19 and 20. This is going to be 5.4, 5.5, 5.6, and talking about what they call the empty models, basically getting predictions. And so we'll cover this material. Looks like 5.4 is a typical section. The last two are a little bit shorter, but I didn't really see fit to put 5.7 in quite yet. We're pretty much right on schedule. And let's just see what we can get out of this particular section, especially as far as R is concerned, and some of the stats behind all of it. The mean of the sample distribution is the best unbiased estimate for the mean of the population. So that's the one number they pick, and on the video she has coming up, you can definitely see that she makes a big deal out of that. So if all you have is the number 62, and that's really all the information you have, that may as well be your prediction. That's the sample mean. That would be the best prediction for anybody else that comes along. In the absence of any other information, that is, which of course is what we would like to get if possible. Well, anyways, they predicted, they put for 6 people a thumb length of 62 millimeters. And they go through a couple of hoops here, which you can definitely read. But we're going to be looking at the prediction, basically, to boil it down. The top row in the output above is the student number from number 1 through number 6. The bottom row is the predicted thumb length for each student. Kind of dull, kind of boring, but that's all we can do in the beginning. And what do you think the predicted thumb length is the same? Well, that's the one number we have, and that's the one number we're going to use. Yeah, we already know their actual thumb length, so it does seem a little bit backwards, but we're kind of going back in the time machine just a little bit just to see how the thinking process evolves. And yeah, it does start with the one number, and we're going to try to adjust that number, of course, a little bit, but in the next chapter they'll have more to say about that. To use these predicted scores as a way of seeing how much their error might be, because obviously everybody doesn't have the same thumb length. You would have to save the prediction for each student in the data set, and they go through all of that. And we save the predicted score for each student in a new variable called predicted. Then you could subtract the actual thumb length from the predicted thumb length and get a deviation, sometimes called an error. Is the deviation. That's how far you are away from the average. Unless you happen to be exactly 62, and then you're sitting right on the average, and that deviation is 0. And that can happen, of course. So let's modify this command. Maybe I can expand this for those of you who can get a better look at it. Well, I'm having a little trouble with that today. So anyway, let's just go ahead and get into Tiny Fingers $ predicted. They'd like us to modify this to save the predictions from the tiny empty model. They have the funniest names for these data sets. Well, the point is, the predict, as they just said, predict command with parentheses is how we get started. We have to put the tiny empty model in there. So make sure you capitalize empty and put dot model. It's just the way they titled it. They have long names for these things. I prefer much shorter names, abbreviations, just a little bit easier to do in my opinion, but that's not what they have for us. And then, of course, the command which they've already put in here simply prints out what's in Tiny Fingers. So, yeah, just leave that one alone. And let's go ahead and run it. Of course, you can check the hint out. But what it's going to do is pretty much the same as before, except now it has the actual thumb length of the 6 students along with their predictions, which across the board is 62. And you can get a better look down here as to what's going on. And yeah, this does seem duplicative. The student ID is the same as the other ID. Well, whatever. So look at the printout of thumb lengths and predicted thumb lengths for each student. Which actual scores were closest to those predicted by the model? This is a very easy one. I will not give you any hints, but clearly you want to get the numbers that are closest to 62. And if there's a tie, I would pick them both. And it'll tell you the answer right away anyway as you submit it. Be sure to submit everything you do so you can get credit for the participation, obviously. I should have made it more than 5 points, but anyway, the idea is for you to participate in this so you can understand what's going on. I don't understand how anybody would get it without doing this unless you've already had some experience doing R. There might be one or two of you out of 120 that have had some experience doing R, but I don't think it'd be very much more than that. Well, we have the idea of the mean being the simplest model of the distribution of a numerical quantitative variable. And of course we have data equals model plus error, and so they have that and they change it around. They want to focus on the error this time. And so just by subtracting mean from each side, data minus mean is now equal to the error. And they also, by the way, switch sides, but that's no big deal. They focused on the error. And if you take the data point minus the mean, that is the residual or the error or the deviation, so many names for the same thing. I know that can get confusing. But they have slightly different words for slightly different contexts, and they're kind of bouncing around between them a little bit in this class. So the 68 has an error or deviation of 6, plus 6 if you want. And well, you should put a sign on it, be consistent. If you're above, that seems like a natural one to say positive 6. If you're below the average, it should be a negative, and that's perfectly fine to do it that way. And yes, they bring up the word residual. And we can then find these errors by what's being used here in R as tiny fingers $thumb minus tiny fingers $predicted. So that gives you the data, the thumb data, minus predicted, which is the mean. And they've run it already, and they find the values for these 6 people arranged in order. The first person was 6 millimeters below average, all the way up to 6 millimeters above average. And of course, you see the 2 close ones right there. And closeness doesn't count as far as the sign is concerned. So if you're off by 1, you're off by 1, whether it's above or below. The numbers in the output indicate for each student in a data frame what the residual is after subtracting out the model. So we can modify this and use exactly the same command to figure out what the tiny residual would be. Tiny fingers $ residual. So I'm simply going to save a little time and copy this. You can do the same and slip it in here, and that will actually give us the residuals, the data minus the predicted, data minus the mean will equal the error or residual. And of course the printout, very simple, just make sure you type in the data frame tiny fingers, and let's take a look at the hints, just see what they said. Subtract thumb from predicted. Of course, they kind of got that wrong. It's predicted from thumb, so it's really thumb minus predicted. Anyway, sometimes the hints there are a couple of glitches in this buff stuff, but now you can see in a better view down below how the residuals were actually calculated. In case you didn't know where the minus 6 came from, that person's length is only 56. Subtract 62, you get negative 6. 6 units, 6 millimeters below average, etc., etc., etc. And you could also call these leftovers, all kinds of words for the same thing. They're so important in modeling, there's even an easier way to get them in R. And so we use the results of our model fit, which we saved in the R object called tinyempty.model. All kinds of weird names, but anyway, they've saved it by typing in the resid command, resid. And that's going to be tiny empty model, so they've already gotten that, and that's a little bit faster way to go. And get the same numbers, but instead of specifying the data and model's predictions, we can just tell R which model to get the residuals from. Modify the code to save the residuals that we get from using resid function in the data frame and call it easy residuals. That's what they did. Modify this to save the residuals from that model into calculating from the easy way, which they've already done for you. You don't have to set up any subtraction. They'll just do it for you, which is nice. And it's important enough that that does make some sense. So once again, I'm just going to copy and paste, because they've pretty much given us the outline here. We just put it into the residual command, paste it there, and of course we print it out with tiny fingers. And well, what do the hints say? Use residual function. Yes, of course. So let's go ahead and run that. And easy residual means that it's just done basically for you, but it is nice to see how to do it the long way. Not that you'd want to do it the long way, but at least it tells you where the numbers came from. If you just start blindly finding stuff without really knowing what it is, well, that's a recipe for disaster. So we don't want to do that. We want to have some kind of understanding, obviously. And so you can see the better picture, and they've got residual and easy residual together. I didn't happen to do that, but notice how they are exactly the same. Just use different methods to get the residuals. With only 6 students here are the thumb lengths. We looked at this briefly before. The predicted is one number. Kind of a boring graph. Notice the count is suddenly 6. That may be a little difficult to see, but that's a 6 instead of a 1. So a little bit different scale. And then the residuals have the same shape as the first graph. They're just centered differently. So they put the center at 62. Here the center was at 62. So they've just taken the scale here on the x-axis and subtracted 62 from every single number. Now they may not have picked the same scaling points. That's fine. But the 0 was where the 62 was. And so that would be a 3. 65 minus 62 is 3. But they chose a 4. No big deal. It's still the same shape. So what does the distribution of thumb look like? Well, just as before, it's kind of scattered about the mean, somewhat symmetrically, by the way, because these are very close to the mean. We've already looked at the residuals already. The distribution of predicted is rather boring. We normally don't think of that as much of an issue, but it's good to see it once. And after you subtract that 62 from everything, we just said the residuals are the same shape exactly as the thumb, and different numbers. It's all been shifted by 62 units. So what's different about the distributions of down there? They've been shifted by 62 units. Yeah, and what is similar? The shape is exactly the same. The the lineup of how the distribution of the data lands up is still, you've got the same gap. The picture's worth 1,000 words. You can just tell by the picture how they look the same. It's the scale that's changed. Okay, the distribution of the data and the residuals have the same shape, but the numbers on the x-axis differ across the distributions. And so we have it centered at 62, and the distribution of residuals centered at 0. That's what I meant about the shift of 62. Data that are smaller than the mean have negative results, but those that are larger than the mean, such as 73, have a positive residual, such as 11 if this was on the data, but it's not this time. So now favstats could be done here. So I guess what I'm going to do is make sure we get all the favstats done. So got favstats, parentheses, and inside there we would have to talk about the thumb. That's the variable in question. And data is from tiny fingers. They have to keep being reminded of that. I guess their memory isn't very long. Let's make sure it's spelled correctly. And that takes care of the favstats for thumb. And we do the same thing now with residuals. So we're doing 2 for 1 here. But this time the only change is tilde residuals. Residuals, of course. And then data equals tiny fingers. Okay, and if you decide to save them, you could print them out. Well, that's something they didn't seem to do, but you could just simply type in tiny fingers, I guess. Let's look at the hint, and don't forget thumb and residual, and then we'll run it. And object residual is not found. Okay, why is that? I'm not quite sure. Worked yesterday, famous last words, data, tiny fingers, anything misspelled. Don't see anything misspelled, so let's submit it. And did you produce the same output as favstats? Well, no, I don't know. So let's see what I did wrong. It doesn't show me anything that I've done wrong. So the solution is exactly what I typed in. And yeah, it does actually produce the same output as favstats, tiny fingers, residual, $ residual, but this time they were a little bit unclear as to what they were looking for. So don't sweat it. Don't sweat the small stuff. I've already done it for you. And yeah, sometimes I'm perplexed as the small errors they may have made. But this is the output that we actually did see up here. Saw it twice actually, and the upper output is the same. All the numbers 56, 60.25, the 62, etc. The 5-number summary, then the mean, which we already knew about, standard deviation, which we're not really using, and n is 6, etc. This is something else that we have not gotten to yet. But R is very precise, and it turns out that the residuals should be centered at 0. Should be centered at 0, but it's not because it apparently had some round-off error. this number, as they're talking about, is extremely small, may as well be 0 for all intents and purposes. This is a number very close to 0, 10 to the minus 14th. That's what, 100 trillionths? Yeah, so there it is in all its glory. Lovely number there. And yeah, that's a number that's just due to round-off error. Do not worry about that. I wish they would. You could probably specify a tolerance and just call it 0 when it gets below a certain number, but we're not going to get into that kind of detail here. So just read it as 0. And this time it really would be 0. And these other numbers are actually more informative. The -6, the min, the max, we actually saw those numbers already. One thing we didn't see was the 1.75 plus and minus. So the standard deviation is exactly the same. It really is the same data. It's just been shifted over by 62 units. So once again, they've been shifted over by 62 units. And they are the same exact shape, spacing between all of them. They're just 56 minus 62 is minus 6, etc., etc., etc. This number is 0. Should have said 0. A weakness in the programming. And so, yeah, the residuals always sum up to 0. That's a fact. We could have looked at some of the other numbers back here. Let me see if I can find them quickly without wasting too much time. These numbers here, minus 6 cancels out with the 6. The minus 2 cancels out with the 2. They zero out. Minus 1 and 1. Of course that adds up to 0. That's a definition. All residuals must sum up to 0. Even though they didn't quite give us exactly 0. Don't worry about that. So now we have another R situation, and this time we'd like to explore the predictions and residuals from the empty dot model fit earlier from the full set of fingers data. Add them as new variables, predicted and residual, to the fingers data frame. So this code from before fits the empty model for fingers, and it's going to be kind of a variable, a linear model. Thumb is null, so there's not much happening there. The data comes from fingers. So generating predictions from the empty model, let's see what we could do. We can use the predict command, as we just saw. We'll have to put parentheses, of course, and we'll predict empty dot model. That's all. So there it is. And residuals, same thing, assuming it works. There we go, getting too low. Residual, and that is a singular name. It's not plural, not residuals. Maybe that's the mistake I made earlier. But now this will print out 10 lines of fingers. In other words, head, select, and then fingers, thumb, predicted residual. But instead of 6, we put another number in. If we want some number besides 6, they changed that to 10. We looked at that very briefly before. Oh, by the way, the hint says use predict and resid. That's no big deal. Let's go ahead and run it. So if I can X that out, if I could, they'll let me. There we go. So let's run that and see what we can do. Doesn't like it. Okay. Not my day. Oh, of course, I didn't use, well, no, not supposed to be, well, yeah, I guess it is supposed to be capitalized, or is it? Capitalization can be a very weird thing, so, yeah, resid, no, they're lowercase. Resid is lowercase, predict is lowercase, yeah, so don't know what I've done wrong here. Maybe it's storing my answers from before. I'm not quite sure what's going on, but let's go ahead and submit this. I apologize. This worked fine yesterday. So residual, do they want capital? Yeah, apparently they want it capitalized. Really don't know why. Let's see. Nope, not capitalized here, but over here it is capitalized. Go figure. Go figure. So this is what I typed in before. Empty model. The first and fourth lines are given to us. It's the second and third lines that are not. So I did predict empty model, predict empty model, predict empty model. Oh, resid, not residual. Yeah, okay, there we go. It's resid. I forgot. I'm so sorry. Anyway, so let's run it now and see what happens. Now suddenly the whole thing pops up. Very good. Now as I X this out, even better, take a look down here, which is the same. We have a prediction now of 60.1 and the residual about 5.9. This person is still above average, but the prediction is different because we have a different set of people. And we're only going to use those 10 people. Somebody with a 74 thumb length is 13.9 above average. That's a lot. And somebody with only a 55 is, or even a 52, is about 8 units below average right there. And of course, we can do histograms with the GF histogram command. So let's do that, underscore. And so we have that along with the variables. This time we'll start with thumb and continue with the data equals fingers, which has to be specified every time. Okay, and continuing. Same thing for predicted, so this part will be just repetitious. And we'll type in the rest of it. I probably should just copy this. And this time we'll take predicted as our variable. Data equals fingers. So, okay, this time I'm just going to copy it and paste it. So, and see, and then we'll change that to residual when we get down there. So as I copy it and change predicted to residual with a capital R and get it to run. There we go. So we have 3 different plots, and these will be better shown down below as they typically show you the answer right away. So here's the thumb length. We've seen all this before. There's nothing new about this. This is the histogram of the thumb lengths, ranging from around 40 to around 90 millimeters. The predicted here looks like 60.1. It's a different sample, so we're having a different prediction. And the residual now is over here. Same shape as before, and I assume it's centered at 0 because we're using the entire data set, yet we're using only 10 to generate the sample mean. So it may be not perfectly accurate, but they're showing how, for sample means, the data itself will look the same as the residuals in shape. It's just been shifted. So this may not be perfectly centered at 0, but that's okay. It's close enough to the 62 that we saw earlier. So let's get into the shorter sections that follow this one. And 5.5 is called Venturing into the World of Mathematical Notation. Okay, we had the word equations, thumb equals sex plus error, and so on. All of these follow the form data equals model plus error. So data was thumb, model was sex or gender, and error, of course, is the deviation. That means that not everybody is exactly average. So all the words are nice to get started with, but we don't continue with that very often. We would rather abbreviate and use formulas, and some of you may have seen some of these types of formulas before, and others may not have. The only prerequisite for this class is intermediate algebra, so you may have seen just a little bit of it. Those of you who had more math than that would have seen more, of course. And we've used a word type of equation for the mean very often. This is the way I think of it anyway. You add up all your numbers and divide by what they say the number of numbers. I'd rather say quantity of numbers. Quantity of numbers makes more sense. What is n, in other words? So number of numbers does look a little bit off-putting to some people. And of course you divide. Then they go into this notation, which looks a lot more complicated, which can be explained. And some of you may have seen this, many of you may not have. And there is a shorter version of this, by the way. Take a deep breath. No need to panic. Yes, math is so scary. I know. It just scares everybody to death. Well, a lot of people anyway. But you're all college students, so you shouldn't be that afraid of this stuff. It's really pretty simple when you think about it. Let's unpack this equation piece by piece. The letter y is going to be representing the outcome variable, very typically done as y. And we'll do that throughout the course. We put a bar over the y, and it just says it's the mean of y. The mean of y, typically a sample mean, by the way. And the Greek letter sigma, this is something you may have seen before, pronounced capital sigma. We do have a lowercase sigma, which we're liable to see later, but this is the uppercase capital sigma. And it should be read as the sum of. It's a summation notation. In other words, we're adding up all of these things coming up. N, of course, we've seen before, is the letter used to represent the size of a sample. So yeah, whatever it may be, whether it's 10 or a lot more than that or even less than that. Finally, we can use the subscript I to represent each individual, I for individual, observation in our sample, starting with observation number 1, going all the way up to observation n, whatever n may be. Some number undoubtedly larger than 1. So in the equation above, the expression to the right of the equal sign could be read as the sum of all individual y's from 1 to n, that's what the I equals 1 up to n, so it's going from bottom to top, and then divided by the number of observations, the number of numbers, as I said before. That could be 10 or some other number. Seems like a lot of notational baggage, and so a lot of the time you can write this a little bit more simply, or at least in a slightly more organized way. Notice the summation sign here has the I equals 1 down below and the n up on top. It's just saying go from 1 to n, a very typical request. So typical that sometimes the notation is just skipped on that level, and we just use the sigma instead, because if you said the same thing 500 times in a row, everybody kind of knows what's going on at that point. So when they say the sum of all numbers, which numbers exactly are we referring to? The outcome variable, the y, or the x, explanatory variable, the x? So using the notation y makes this clear, because you could be summing up the x's. But as a minor detour, let's go back to one of the properties of the mean that we previously discovered using R. If you add up the deviations, you should get 0, and that's what this is saying. Well, y sub I is each individual observation. Y sub 1, y sub 2, y sub 3, etc., all the way to y sub n, the last one. But each time we subtract the mean away. This is just doing the deviations. We did that already. Predicted residual, subtracting, and yeah, when you add them all up, you're supposed to get 0. Not 10 to the minus 14th, but 0, exactly. And round off error might sneak in once in a while. Examine the equation above. Which verbal statement best describes the meaning of this equation? Well, we just kind of put that into words, so you should be able to pick which one it is. And by the way, any number divided by 0 is not equal to 0. It's undefined. Some people make that mistake. I don't think that's going to be an issue here, but I've seen that a few hundred times in my career. People think, oh, divide by 0. So if you use anything on your calculator, divide anything by 0, you're going to get an error. And in college algebra, they would explore that more, but we're not going to be doing that here. So anyway, go ahead and try that one out. You'll get the answer immediately. There are two things we need to understand about notation, things that most students never fully appreciate. And the mathematicians know quite well. Of course, they are much more experienced with it. There's no single correct way to use notation. Different textbooks have different notation, especially in statistics. And in algebra, it's a little bit more cut and dried. In fact, a lot more cut and dried than statistics. It's still an evolving science. It's only about 100 years old. And math is only several thousand years old. Think of the Pythagorean theorem going back to 3000 BC, something like that. And yeah, statistics is a youngin' compared to the math world. Well, anyway, different formulas have evolved differently, and they're starting to settle down more and more, but there's still some discrepancies here. And we could take a look at the mean formula. There's an example, and this could be written a lot more simply, and I'm a fan of this. If you have y bar, which was the mean of the y's, we could simply add up all the yi's. Who cares about this I equals 1 to n business? That is so commonplace, it's frequently dropped, as I hinted earlier. Don't forget to divide by n, however. Now, this is a lot faster way to do it. Just grab all the y's, sum up all the y's, divide by n. Period. The rest of the notation, not particularly necessary. So, yeah, people do get tired, believe it or not, of writing all the extra notation down. Shocking, I know. But they just agree to drop it, because if they needed to go from like 2 to n or 3 to n minus 1, they would say so. And they don't, which is practically never. That is, we would always go from 1 to n, just about. And so sum of all of them and divide by n. But we want to be consistent, and so here, though, they are exposing you to different versions of the same idea. And here's a hint for you. Only one of them doesn't work. Only one of them doesn't work. Keep a careful eye as to what you're summing and what you're not summing, and you'll find that one of these is kind of going against the grain a little bit. So, yeah, n doesn't need to be summed so much. So if you're trying to sum up n, there's something kind of amiss on that one. So I'll let you find it. But anyway, the other thing about math notation is there are two different ways of interpreting it. Most students look at notation as a step-by-step recipe for how to produce an answer. So to find the mean, take all the numbers, add them up, and then divide by n. And there's a more powerful way to look at notation like this. It's a representation of a quantity or a relationship. And so they're saying, take a simple example, 2 plus 3 could be seen as a recipe. Take 2, add 3 more, and you get the answer 5. But it could also be seen as a quantity in and of itself, just 2 plus 3. And not only that, if you have x, you could look at x plus 3. So if x is, say, a current year, 3 years from now, will always be x plus 3. Your age, exactly 3 years from now, will be 3 years older than you are now. So if you see this as a recipe and you don't know what x is, you're stuck. But if you look at x as just being a general term from which you can just add 3 to it, 3 greater than x, even 3 plus x would work the same way. And yeah, parentheses, sometimes they're not even necessary. Just say it, and then you're good. So if you think of notation in this second way, representation of quantities and relationships, you can do better overall, I think. So when you see an expression that represents the mean, don't think of it as a handy set of instructions or how to calculate the mean. You don't have to start calculating it. You just start using it. And FaveStats, by the way, will do this kind of for you. Think of it as an important relationship that defines what the mean is. So think about what it means and look for patterns and so on. And we go to the final section of today, a comparatively shorter lecture, I believe. Data equals model plus error in notation. Let's see how the math notation is used to represent this simple empty model that we introduced before. We introduced the overarching concept that data equals model plus error. And in our simple model, we're using one number, the mean, to model that distribution of scores. And so we could say thumb data is equal to mean plus error. Yeah, you could do that if you want. Yeah, mean is the model and error is the model. So they're just kind of transferring data to thumb data, model to mean, and error they're leaving alone. And there's some real advantages to writing it in mathematical notation. You don't have to use so many words. And the individual y, and by the way, sometimes they just say y, but here we better say y sub I, just to be consistent with their notation. But the y bar is definitely always the mean. And here's the error. And this is called e sub I. And I'm thinking that e might be enough, but let's be consistent with their notation, and e sub I is a better way to go. So it represents what we've been doing with r, and it says that each value of y sub I, which is y sub 1, y sub 2, y sub 7, y sub 17, all the way to wherever your last number would be. It could be as the sum of two parts. The mean, which we've already calculated and found what that was. Usually we've already calculated that is. And each time we have the deviation each time that's added to it. So to find your particular value, we take the mean and add the deviation or the error, and then we see what that value is. Maybe it's yours, or maybe it's somebody else's that you're looking at particularly. And so they switch them. And they say that y sub I, well, they do this switch up, and we also see a version that looks like this with a y hat. Now that's not the mean. It looks very close to the last equation. Now instead of y bar, we've got y hat, also with an I on it. And we could think of this as the model's value for y. The equation simply states that each value of y can be seen as the sum of its predicted value and its deviation. So later on, when we make predictions, we can then connect that to the error. In our tiny data set, student number 1 had a thumb length of 56. So y1 is 56, period. Now, under our simple model, we use the mean as the predicted value of all students. So here, y hat number 1 is y bar, which is 62. There's not much going on here. It's one size fits all. So y hat number 2, y hat number 3, they're all 62, at least for now. And yeah, we could put the E1 in this case, and it'd have to be minus 6 to, bring it to where it's supposed to be at 62. So let's represent student number 1 as data equals model plus error. So we have our more complicated formula with a hat on it, which is a prediction, not necessarily the mean. And we could go ahead and figure out what to do with this one. So we have all these possibilities, and yi is what we're starting with. That's going to be your thumb length. So you could click and drag over there. Then we also have the fact that we have all these other choices, and average residual models prediction for student number 1. That looks pretty good. It did say something about a prediction, and I think that's the only one that has the word prediction in it. So that's got to be the second choice. And then E, of course, is some kind of error or residual. And so we would have to look at that and how is it different? Yeah, they didn't use those words, so let's just see how different the model is from student number 1's thumb length. So that would go into the third category. So experiment with those and see how it goes. Why is there no subscript for y bar when there is for the other two? Well, y bar is just the mean, and that's not going to change. No point in putting subscripts on them because they're all exactly the same. And it does kind of reinforce the fact that it's a standalone number. As we develop more complex models, we still end up with a single predicted value of y for each score based on our model. And we can do individual predictions, which are not just 62 across the board. We can say, given certain data, we think this person will be a 61, that kind of thing. But we predict this value using more than just the mean. That's later on. That's not today. We'll get to that another time. But for now, we can complicate things a little bit more, introducing one more form of our data equals model plus error formulation. This happens to be called the general linear model. I've seen this before. But anyway, based on what you've learned about notation so far, why do you think the B0 might represent in the equation above? Well, what's missing here seems to be the predicted value. The B also looks like y-intercept, but that's, I guess, some coincidence right now. There's a more abstract version of the equation above. We substituted B0 for the mean y bar. Don't be concerned if this doesn't make complete sense. We'll be working with this a little bit more. This is one of those things that will take a little time to understand, but B0 can represent the mean, but it doesn't have to. Right now it's going to, but anyway, the empty model, it represents the mean, but for other models and other situations, it can represent other values. It could be categorical values, and it could be the mode, for example, although it'd be a little tougher to try to do this with categorical data, but it could be done, I suppose. And so this flexibility is what makes this general linear model general. And that's okay. So we have the GLM model statement. You should think carefully about what in this particular situation each symbol represents. So using our thumb example, try to interpret this GLM notation by mapping on to the contextual interpretations. So what we are trying to get done here is to look for the thumb length, and I always put little i's there. It looks like thumby, but it's not. It's thumb sub I. And so yi, yeah, that's your thumb for sure. And then here we have B0, which was called the mean. So we're going to continue to call that the mean, even though it does look a little bit cloudy. It's quite a bit more generalized and not necessarily the notation I've seen in some of my books, but that's okay. Of course, E will be the residual, the last number there. So that's the error or residual. This is the only one that doesn't look like it makes perfect sense to me, but that's the style they're going to use here. Now try to interpret this GLM notation of our data equals model plus error statement. So yeah, it's kind of the same idea here, but they've changed the words around. So now we've got data of the thumbs for the first, and then obviously the error, so I would just kind of do the easy ones first, and E, of course, is the error or residual or deviation, so many names for the same thing. And then the prediction or model, I would say prediction for that. And it doesn't have to be the mean anymore. It could be something else, although we're not liable to see that for a while. Now she has an excellent video here, which I cannot get the sound out of, but you can at least you can see a little bit of stuff here. Let me just click on a couple things, and you can see here pictures that we have. And she goes through and shows you the deviations and all. So you should go ahead and try that. Okay, so there she is. That's our author, Xi, and she's very good. And anyway, that's the 3 sections there, a couple short ones. We could get like a preview look at the next one. It'll let me do this in student mode. It's a little bit different than instructor mode. Just click on next and see what we have in store for us, the live lecture next Wednesday and Thursday. Statistics and parameters. There's an easy memory trick as I jump ahead just a tiny bit. Uh, Statistics come from samples, and S is the same as S. Keep the same letter. Parameters come from populations. P is the same as P. So parameters are kind of set in stone, whereas statistics are what we usually work with because we usually just get samples. Even the census can't get everybody. I hear about a 60% rate of filling out their census forms, and how Montana kind of got screwed on the representations, probably because they're only getting 60% of the people filling it out based on best estimates. But anytime they try to use those estimates to project ahead what really is in a state, it becomes a political football. Some parties don't like it, and some parties do like it, but they never can settle on anything. And the Constitution does say it has to be an exact head count. So if you haven't really gotten the head count, then it's really plus or minus a certain amount of error, or residuals, I guess you could say. Anyway, we'll go through this and a couple more. I think I'm scheduled to cover at least 3 sections, depending on the length of them. Could be 4, but I believe I'm trying just to do 3. Try to get to chapter 6 by the time our next test comes along. Okay, so remember the office hours on Wednesdays, 4 hours on Wednesdays, and we'll be talking more to you on that day, Wednesday and Thursday, depending on your class. And meanwhile, have a nice weekend. It looks like the weather's cooling off. I'm happy to hear that. So, and go Dodgers. Bye-bye.